Hello everyone. We will continue our class of techniques for circuit analysis. Let us recap the concept of the supernode. When we have a voltage source directly connected between two essential nodes, we basically have a supernode, as you can see. In this case, we can treat the two circuit nodes as a combined single node. If you take a look at this red boundary, all the currents entering or exiting this red boundary should be added together and their sum should be equal to 0. So basically, we apply Kirchhoff's current law to this region. And all the currents entering and exiting in total would give 0. Okay. So if we establish the circuit equation at node 2, it's using the node voltages approach, and we have the current dimensions and the voltage directions have been determined. We can see that the current through the 5 ohms resistor can be defined as V2 minus V1 divided by 5 ohms. Okay, this is the current, and since it's leaving this supernode, it's going to have a positive sign in front. We have another current, and since the voltage 2, V2, is defined like this, it's obvious that the current direction is towards the reference point. So its current value is V2 over 50. Okay. Normally, if we were not going to use the supernode equation, I also need to include this I, which is the current of this dependent current source. As it's also leaving the node, I also put a positive sign to it, and their sum should be 0. This is the KCL at node 2, okay? I can also construct a KCL at node 3, as you can see. Now, since this current is entering the node, it will have a negative sign because of that, minus I. And since the I phi is defined as the current through the 5 ohms, I can calculate this value, or we have actually for the node 3, we just need to know 3 currents. The first one is the I that's entering, which is the unknown. The second one is the current leaving this node through the 100 ohms resistor towards the ground. And also an independent current source whose current is entering this node. So they should sum to 0 according to the KCL at circuit node 3. If we write down the equation, we will see that this holds. Okay. If you combine the equations from node 2 and node 3 by adding them, basically you see that this I is destroyed. So by the concept of supernode, we simply get rid of one absolute unknown in this case. Like when we have this voltage source here, we don't know its current. It will be solved as the last element in our equation system. So if we are able to write the whole equation using a supernode, we are just accelerating the solution. So if I directly write, if you sum these two equations, as you can see, things will be cleaned up, and we end up with an equation which resembles this. Now, if we treat the whole region denoted in red as a big circuit node, the KCL at this node still holds. And because, but it requires the existence of a voltage source between two nodes, nothing else. As you can see, we have a voltage source here between two nodes. So if I add the currents that are leaving and entering the nodes, they should be equal to 0. And this is actually the combined two equations generated by the KCL at the second and the third circuit nodes, as you can see. We also have an auxiliary equation that's defined by the terminal equation of the dependent current source. It depends on I phi, which is defined as V2 minus 50 over 5. We simply have the V3 as V2 minus 10. Okay, let's continue with the next slide. In this example, we observe another circuit which has 4 essential nodes. As you can notice, we have 3 connections here at node A, and we have 3 connections at node B, and we have 3 on C and 3 on D. We have to choose a reference, so none of them has extra advantage, so I arbitrarily choose the D as a reference node. As a tradition, we typically choose the bottom line as a reference point because it has the highest potential for maximum number of connections. Okay. Here we have an two independent sources and one current dependent current source, as you can see. So here what we observe is between the B and C nodes we have the independent voltage source, and here it creates a supernode. Actually, another supernode can be written between A and D, but since we have chosen D as our reference point, that can be omitted. And if we focus to this, supernode, and when we define the node voltages VB and VC, we can simply write down an equation that defines the Kirchhoff's current law applied to this supernode. First of all, we have VB over R2 as our current leaving this node, so it will have a positive sign. We have VC over RE as another current leaving this node. As you can see, these terms have positive coefficients. Okay. Then I also have a current leaving the node VB minus VCC over R1. Okay. And another current that is beta times IB that is entering into this node, so it will have a negative sign. This should sum up to 0 according to the Kirchhoff's current law. Then for the VC, we can also see that VC equals to beta times IB plus IB. As you can see, IB is the control current, and it's the current of this voltage source, which is the absolute unknown for the time being. But since they add up at these circuit nodes, the current through the RE will be 1 plus beta times IB. So the voltage at this node can be expressed like this. And we also know that there is some relationship between the VB and VC. The VB minus VC equals to V0. As you can see, the voltage difference is basically the value of the is equal to the value of the independent voltage source. So this would give us another equation. From here, we can get rid of VC first. Then we can get rid of the IB as well, because actually we are interested in finding the node voltages. So IB is the absolutely unknown thing. So we can use some mathematical algebraic manipulation to get rid of IB. Once I can express the IB in terms of VB or VC, I can plug it here and then solve the whole equation. If I do the math, I'm going to get this expression, okay? It's VB times 1 over R1 plus 1 over R2 plus 1 over 1 plus beta times RE equals to VCC over R1 plus V0 over 1 plus BRE. This is the basic equation that would help us to find the VB. As you can see, I am assuming that we all know the values of R1, R2, the coefficient beta, RE, VCC is also known, and V0 is also known. So as you can see, the only unknown is VB, so that we can simply solve the VB from this in closed algebraic form. Then once I know the VB, I can put it here to find the VC. This equation will help me to find the VC. And once I know the VC, I can simply find IB from here. So, basically with the help of the supernode, problem is reduced because we reduce the number of nodes. As you know, we need to create equations as many as the number of nodes in order to solve the circuit uniquely. So supernode actually is helping us to save some time. Okay. There are also other methods that allow the analysis of circuits. Okay. Here, let me introduce you the mesh current method. Basically, we focus on two methods: the node voltage and the mesh current. For the mesh current, method to be applicable, we need to have a planar circuit. It's only applicable to planar circuits. The node voltage method is more universal. You can apply it to any circuit. Still, there are occasions where mesh current could be advantages. So first of all, let us see how many branches we have here in this example circuit. We have, three essential branches. We have two, essential nodes. And so the BE minus NE minus 1 equals to 2. This is the number of mesh equations that we shall have. So in this case, we identify the meshes inside the planar circuit. Here, there are actually three loops. The first is the outer loop, and there are two additional loops. But the outer loop can be decomposed into smaller loops, so it's not a mesh. But the inner loops cannot be decomposed into smaller meshes or smaller loops. So these are called the meshes. Okay. We have two meshes here, and we need two meshes actually, two mesh equations to be able to solve this circuit. So we assume that there are fictitious currents flowing in these meshes. Okay, let's say the one is IA and the other is IB. Now, next step is expressing all the branch currents in terms of these mesh currents. Okay, so for instance, I have I1. Since the direction of the I1 and IA is the same, I1 equals to IA. And for I2, since it's in the same direction as IB, I2 equals to IB. But for R3, note that two currents are flowing at the same time and they are opposing each other. So the I3 should be equal to IA minus IB, as you can see here. Now the key point is mesh current method is based on the Kirchhoff's voltage law. Okay, so the Kirchhoff voltage law tells us that in a loop, in a closed loop, the sum of all the terminal voltages of the elements, circuit elements, should sum up to 0. Okay, so we choose a rotation direction, and while rotating, we, depending on our polarity, we write down the voltage drops over the elements and we sum them to 0. So here, minus V1 plus IA times R1 plus IA minus IB times R3 should sum to 0. And if you move V1 to the other side, you are going to get this equation. Okay. And for the IB, we can write, since the rotation direction and the polarity of the voltage source are in line, it will have a positive sign. So V2 minus IA minus IB times R3 plus R2 times IB should be equal to 0. Here, the V2 can be moved to other side as minus V2, okay? And the minus IA minus IB, this current, can be rewritten as IB minus IA. Remember, my chosen direction is towards the reference point, and IB is opposing it. This is why when I'm writing the second equation, the voltage drop will be negative, and because of that I put a negative sign. But here in the equation, it's reflected inside the parentheses so that it became IB minus IA. So I have two equations and I have two unknowns, IA and IB. If I know all the values of these components or elements, then I can uniquely solve this equation. Once I have the IA and IB, then I can express all the real circuit element currents from them. And then, knowing the voltage drops, I can calculate all the voltage values across the components. And once I know the voltage and the current, I can also establish the power calculations. Okay. What happens if we have dependent sources? Well, it depends on, but finally, the rule doesn't change. It's universal and it's applied. So whatever you have in the circuit, the KVL holds, so the mesh current method also holds. Here, as you can see, we have many loops, but out of 3 can be classified as meshes. And for each mesh, I can put a fictitious current. Let's say I1, I2, and I3. All of them are flowing in, clockwise direction. There is an I5, which is the control current for this voltage current controlled voltage source. Okay. Then I can simply write down my equations. So here I have the 50 volts minus 50 plus 5 times I1 minus I2, because the current of this element is I1 minus I2, okay, because they are two neighboring mesh currents. So their difference is, since they are opposing each other. If I2 was rotating in the opposite direction, then I had to add them because they are now in the same direction. So rotation directions determine whether you are going to add or subtract the mesh currents for a component. So I1 minus I2 is its current. Okay, so 5 times this value will give me the voltage drop. And I continue to rotate. Here at 20 ohms, I have I1 and I3. So I1 minus I3 times 20 would be equal to 0. And if I move the 50 volts term to the other side, I'm going to get this equation, as you can see. Okay. Now in the second mesh, I only have resistor components, so I can easily write down the KVL equation. So since I'm rotating in this direction, and in the first place, I assumed that the current flow on 5 ohms is from left to right, then I'm going to get a negative sign. Minus 5 times I1 minus I2 plus 1 ohms times I2 plus 4 times, that is 4 ohms, 4 times I2 minus I3, because they are opposing each other, will sum to 0. And since I have a negative sign, I can just redistribute it inside the parentheses to make it look positive, like this. I1 and I2 interchanged. Then the second equation is established. And I can write down a third one using the third mesh. Now, since I have a voltage, current dependent voltage source, and I'm rotating in the same direction, I will have a positive value, 15 I5. This is the voltage value generated. And since I'm opposing the 20 ohms, I'm going to get minus 20 times I1 minus I3, which will be converted to 20 I3 minus I1 if you distribute the minus 1 into the parentheses. And in the 4 ohm, I know that I'm opposing it. So I'm going to get minus 4 times I2 minus I3, which would again translate into 4 times I3 minus I2 because I'm distributing the negative sign into the parentheses. Okay. Then this would sum up to 0 according to the KVL. So I have 3 KVL loops, 3 mesh currents, unknown, and 3 equations. In addition, I have one constraint equation coming from this current-dependent voltage source, as you can see here. And I phi can be written as I1 minus I3, because in the first place we took it like this. This is actually I phi, as you can see here. Okay, so it puts the fourth equation. Now, if I plug this, substitute this here, and rearrange the terms, to put it into a mathematically neat structure, I'm going to get something more beautiful. So let me show that to you. If we do the math, we are going to get this equation set. Okay, make all necessary reductions. Now, how can we solve this? Okay, apparently, as the circuits get complicated and more complicated, we are going to get more equations, maybe much more than a human can handle. For this, we can use MATLAB and use it to solve these equation systems for us. Okay, so remembering these coefficients and remembering our variables, I can simply go into MATLAB and use the symbolic toolbox to help me. What I'm going to do is first I clear all the previous variables, okay, so that everything is clean in the memory. Then I use the sims command to create my variables, the unknowns that I would like to solve. Okay, so I have I1, right? I have I2 and I have I3. These are my unknowns in my equation. Take a look at this. I1, I2, and I3. You can label them as X, Y, Z, whatever, but we just first introduce that these are the unknowns that needs to be, solved. Then I just write down my equations, okay? There was a script that I developed before the class, so in order to save some time, I'm going to copy and paste those. So equation 1 equals to 25 times I1 minus 5 times I2 minus 20 times I3, and this is equal to 50. So for this equal, we use two double equal signs, okay? And this is how we define each equation. So I click enter, then the second equation is entered like that. Remember, we are using double, equal signs to identify the equation side, okay? Then I can simply define my last equation that's coming from the circuit, okay? Now, I have entered my equations into the MATLAB environment. So, using the tools of linear algebra, I can transform these linear equation system into a matrix form. And thankfully, the MATLAB provides a function, built-in function to us to be able to solve any number of equations at once. So the general rule is A times X equals to B, but A and B are matrices here, coefficient matrices. So the X would be equal to the B times the inverse of A, okay? And MATLAB is perfect in finding the inverse of those matrices and matrix multiplications. So it can do things very fast for us. How we approach this is the coefficient matrix is denoted as A, and These denotes the coefficients like these 25, -5, -20, etc. And the right-hand side, known values are denoted by B. Then we can simply say that this should be equal to equations to matrix. This is a function that transforms the set of equations into the matrix form, and then these matrices, there will be two matrices, and they will be automatically assigned to A and B. So at the end of the day, we are going to get a big AEX, A times X equals to B kind of a matrix system in the context of MATLAB. To help the function, we have to provide which are the equations and which are the variables, okay, so that it can resolve. So I have equation 1 that I have previously designed. I have another equation, equation 2, and I have another equation, the third one. And my unknown variables that needs to be solved are like I1, I2, and I3, okay? So when I press the enter, now the system will return an A and a B matrix. So if I say A, I can see it, and if I say B, I can see it as well. Okay, it's a column, a single, 3-1 by matrix, while the A is 3 by 3 matrix. Now, in the last step, since I have now matrices, I can use the linear solve property or the function of MATLAB to get my unknown values, which will be the I1, I2, and I3. So if I use this function linear solve A comma B, it's going to give me a single vector which contains the solutions, okay? I1 equals to 148 over 5, which is close to something as of 3. And I2 is 26 and I3 is 28 amps. Okay, these are the solutions for the mesh currents. Then knowing these values, I can define all the currents of each component or each circuit element. And then I can calculate the voltage drops and solve the circuit uniquely. MATLAB is a great tool to help us to handle the complexity associated with crowded circuits, okay? But here the important thing is being able to establish or obtain the equations correctly. The rest is hard work, which can be handled by computers. But the important thing is being able to build or form these equations. If you make a mistake, even a sign mistake in those equations, the results will all change and will be wrong. As a result, you have to be very careful when you are constructing these equations. Please double check and confirm that you are doing this properly. The best way to get used to it is to solve as many questions as possible, which I try to provide you through the tutorial sessions and also through homeworks and online tutorials on the MyLab website, okay? So this is how we can use MATLAB to solve circuit equations. The same applies if you have node voltage equations. You can also apply it this way. Important thing is to establish an equation system, and in node voltage equations you have to provide V1, V2, V3, so only the name changes, but the structure is the same. So you define your first variables that are the unknowns that needs to be solved, then you define your equations in terms of those variables. Then you transform your equation system into a matrix form, then use the linear algebra tools to solve all the equation system and obtain your unknowns, as you can see. So while you are studying, you can use this method to find the answers of homework questions or any circuit that you encounter. I hope you find this beneficial. Anyways, if we return to our discussion, let me this full screen. And before that, let's switch to the slides. Okay, now we can go full screen. This is the case when we have these, dependent sources. It doesn't really matter. The important thing is being able to establish these equations. And once you have your equations, the rest is, mathematical manipulation and hard work, basically. Let us continue with the next slide. Can there be special cases, as in the supernode case? We can have super meshes as well. So, for instance, here we have another circuit. We have two independent sources and one independent current source, two independent voltage sources. Again, we can identify three different meshes here that cannot be reduced into smaller loops. And all the circuit elements and their currents can be represented with these linear combinations of these three currents. So on each mesh, I can write down a KVL equation rotating clockwise. So I'm going to write minus 100 plus 3 ohms times IA minus IB, because it's current. I choose my direction from left to right. Okay, so I assume that IA is greater than IB. Okay, it's an assumption. Then rotating this, I have some V which is unknown because we don't know the voltage of the current source and we don't know the currents of the voltage sources. So this will be solved in the last step. So I have to take it as it is. Since I am rotating in the same direction, I will write a positive V because the current, I'm supposing that the IA is flowing in this direction and the voltage drop is defined like this, but arbitrarily, okay? And since I'm the same direction, I take it as a positive value. Then I have the 6 ohm, and here I take the positive sign and negative sign here, so I'm assuming that the current is flowing in this direction. Since I'm rotating in the same direction, then I'm going to get 6 times IA, and this sum should be equal to 0. Now I can move the minus 100 volts to the other side, which is 0, so it makes 100. So I can obtain the KVL equation for the mesh A, as you can see here. Now I can write another loop equation here for mesh C, and it's obvious that the 50 volts is direction is in line with the direction of the rotation. So 50 plus 4 times IC minus V, because I'm rotating in the opposite direction, as you can see to this reference. So minus V, and plus 2 times IC minus IB. Here I'm assuming that IC is greater than IB, okay, should be equal to 0. Now in this case I can move 50 to the other side, so it will be a minus 50, and the rest can be written like this. Now let's take a closer look, and if you see that if we sum these two equations, okay, we will obtain this, and we get rid of the V, as you can see. Remember, the same thing happened with the supernode. This will be the super mesh. So within the, if two meshes share a current source, then you can write down a big mesh equation that is composed of these loop. You remove this first, and then you can write down that KVL equation about this big loop, okay? This would give me the same thing. So what is the good side? You get rid of the unknown variable, and instead of two equations, you write one equation, and another equation will come from this mesh, and you will deal with two equations instead of three. This might not sound like a great improvement, as we already have the MATLAB to solve things, but in complicated circuits, this reduces the computation steps, so it can help. So in this case, if we write the last equation for the mesh B, I can say the 3 times IA minus IB. Actually, since I'm rotating in the opposite direction of the current, because I assumed that the current of 3 ohms is from left to right, but I'm rotating in the opposite direction. So it's going to be minus 3 ohms times IA minus IB, which can be converted into 3IB minus IA as a term, plus I am taking the current flow direction for 10 ohms as left to right, so I will add it 10 times IB. And here, again, in the 2 ohms case, I assumed that the current flow is from left to right, so I'm opposing that. Because of that, I should write down minus 2 ohms times IC minus IB, which can be converted into 2 times IB minus IC. I'm just rearranging the terms, distributing the minus 1 into the parentheses, should be equal to 0. Okay, I end up with this equation. And I also have a constraint equation that could help me, because I know the current at this boundary. It's 5 amps and forced. So IA minus since the IA is opposing, minus IA plus IC equals to 5 amps. Okay, from here, IC minus IA equals to 5 can be obtained. Now I have 3 unknown, and I have 3 equations, as you can see: the first, the second, and the third one. If we do the math, you can use MATLAB or whatever, you are going to get these results. So we have 175 for IA, we have 125 for IB, and we have 675 for the IC. So all the currents of the other components are a linear combination of these mesh currents, and they can be expressed. From there, I can write down the voltage drops, and I can calculate all the node voltages and the branch currents, which means that I can actually calculate the powers and everything. That's how we solve using the mesh currents. As you can see, with the mesh currents, it's a bit of a harder task, because in practical life, in order to measure the current, you have to break the loop. That requires a surgery on circuit level. You have to desolder, disconnect the component, and put an ammeter in series with it, then make your measurements. It's a bit of tedious job. Plus, mesh currents doesn't allow you to solve non-planar circuits, so that's a limitation. When we compare these, the node voltages versus the mesh currents, node voltages is more universal, because you can always measure the voltage, as the voltmeter is ideally an infinite resistance components. You can connect it anywhere without affecting, or very little affecting the circuit operation. As a result, once you know the node voltages, you can define the currents as the different voltage difference divided by the equivalent resistance between the circuit nodes. So in practice, the node voltage method is more preferred and more useful. Our computers solve circuits using the node voltage approach, basically modified node voltage approach, and it's universal method that can be applied to a circuit with infinite complexity theoretically. However, as a dual partner, mesh current exists, and we learn this. It's also applicable. At times, it could be useful because sometimes if the circuit has many nodes, the number of meshes can be lower than that. So you may prefer mesh current approach to obtain lower number of or smaller number of equations from the system. Okay, let's continue. So the concept of super mesh, if we go back to our original discussion, comes from the fact that if the two neighbor meshes share a common current source, you can think of it as a big single mesh. Okay, two meshes can be merged as if they had been a single mesh. You can ignore the that component and the variables associated with that component in the middle, and write down your KVL on through the larger loop. As you can see, if you do that, you directly end up with this equation, which we have found by adding the equations, KVL equations, coming from mesh A and mesh C. So if I sum them, I will get the same equation, as you can see. So if you can perceive it, you can apply super mesh or super node technique to reduce the number of work that you need to do, okay? However, if you fail to observe it, no problem. Your equations are still there and you can still obtain it by adding them or manipulating them. They are still solvable. So these cases only make life easy for you, but without them, the circuits are also solvable using the standard approach. So this is all about the super mesh and super node stuff so far. If we compare the node voltage versus the mesh currents, basically the first question is, does one of the methods yield fewer equations to solve? Which one provides more advantage to me? I want to solve minimum number of equations. I don't want to deal with horde of equations, okay? It's horrifying. Thankfully, we have computer tools today, but in the old times, it was all man and, hand and pencil, effort. As a result, people always follow the shortest paths to the solution. So the important thing, which method to use, you take a look at the number of nodes, you take a look at the number of meshes, and then you can estimate how many equations you need to solve the circuit. Remember the numerical definitions in the beginning of the class. You can calculate how many equations you need, then you can decide which path is less painless to go. And you can try to identify if the circuit contains supernodes, because which eases the use of node voltage method. If so, using the node voltage method will be a good choice. Otherwise, if the circuit contains any super meshes, you can also take the advantage and use the mesh current method to solve the circuit by reducing the number of equations. And will solving some portion of the circuit give the requested solution? If you are particularly interested in some portion of it, then you can partially solve the circuit in a way that you don't need to solve every current and every voltage in that circuit. So you can ask yourself which method is most efficient for solving just some portion of the circuit. Now, another topic that we will cover today is the source transformations. Okay, this is an essential part, and hopefully we will be talking about it today. Okay. Source transformations are another set of tools that we can put into our bag of circuit tricks to solve the problems. Source transformation typically involves the representation of a voltage source with a series connected resistor by a current source with a parallel connected resistor. And this transformation is bilateral, which means that you can convert from the circuit shown in B into A or vice versa. So how do we achieve this? From a load point of view, that is the virtual load that can be connected between the terminals A and B, we can calculate a load current, okay? So if I write the load current using a single KVL around this loop, it's obvious that the IL would be equal to Vs over R plus RL. Now, I'm assuming that since the two circuits are equivalent, if I put them into a box and only the terminals A and B can be observed, they have to behave the same way. So in this case, what I do is I know that the IL should be Vs over R plus RL, and here in the second circuit, the IL should be R over R plus RL times IS, because it's basically a current divider, so I can know its value. So from here, from these two equivalents, as you can see, if we equate these two equations and reduce the denominators, then the IS is basically Vs over R. So I can convert this circuit into this one, provided I set the value of Is as Vs over R. And the R here series connected resistor is in this configuration parallel connected. Its value is the same, it doesn't change. And also RL is the same. But from Vs to Is, I can make this transformation. Now this might be very handy in situations where we can use this trick to further simplify circuits that we need to deal with. This is why source transformations are very handy and useful. There are interesting cases. For instance, if we work over an example, use the source transformation methods to find the voltage V0 at this point, and across the 100 ohms resistor, find the power developed by the 250 volts voltage source, and find the power developed by the 8 amps current source. Okay. Now, the interesting thing is when I have this configuration, if we have a scenario like this, in which I have some series connected resistor and the voltage source here, the parallel connection of is 125 ohms resistor doesn't change the total equation, so it can be omitted. The same applies in situation where, for instance, if you take a closer look to this configuration, a series connected resistor to the current source can be omitted to calculate an equivalent source transformation. When I'm going to do some source transformation, the resistor that's connected in parallel with the voltage source, or the resistor that's in series with the current source, doesn't affect my conversion. So I can make the conversion using the 25 ohm and 250 volts. These are the series connected, so I can convert them into a current source if I want. Or I can convert this 8 amps in parallel with 100 ohms into a voltage source in series with some, the same resistor. This is an interesting, result, but it works in theory and practice, obviously. So when I'm solving, when I'm trying to solve the circuit, I can simply put open circuits in the resistors that are connected in parallel with the voltage source, or the resistors which are in series with the current source. Okay, I can omit them. Then my circuit looks like this. Okay. Now they will not affect the terminal equation. This is why I can do this. So if I have this, now I can convert this into a current source with a parallel resistance of 25 ohms, because this is what we have found in previous slides. How much current shall it have? It's easy to see that. If you divide this voltage source with the value of the resistor, it means that we need 10 amps source with a parallel connected 25 ohms, because at the end, the voltage between these nodes should be 250 volts. And if you take a look in this loop, in this mesh, you are going to get 250 volts. So these two portions behave equivalent with respect to from the perspective of the rest of the circuit. Okay. So when I do this transformation, my circuit becomes something easily solvable because everything is parallel connected and I have two current sources. So if we further simplify, since they are opposing each other, the net current flow is 2 amps in this direction. 10 amp, overrides the other party, and the rest of the circuit, the equivalent circuit, is 10 ohms. You can compute the equivalent resistance by 1 over 25 plus 1 over 100 ohms plus 1 over 20, and you take the inverse of it. So the equivalent of this complex network can be represented by a much simpler circuit, which is much easier to handle and to learn. This has an interesting outcome, which we will learn. It's called the Thevenin and Norton equivalence of circuits. Let us move to the next slide to explore it. Basically, Thevenin and Norton equivalents are circuit simplification techniques that focus on terminal behavior. Most of the time when we are dealing with circuits, we focus on certain portions of the circuit, not every node. Inputs, outputs, whatever. So these approaches basically simplify circuits from the nodes of interest point of view. Okay, the focus is on the terminal behavior. So internals do whatever they do, but we only focus on certain nodes, and all the complexity associated inside the black box can be reduced to a single voltage source with a series connected resistor, or that complexity can be reduced into independent current source with a parallel connected resistor. Now the key point is, how do we calculate or these equivalent things? We will learn about it. In the Thevenin equivalent circuit, an independent voltage source is in series with a resistor, RTH, which replaces an interconnection of sources and resistors in a linear circuit. The Norton equivalent circuit is basically a source transformation from Thevenin equivalent, which you learn to find the Thevenin equivalent first, then you can always convert to the Norton equivalent. It consists of an independent current source, ITH, let's say, in parallel with a Norton equivalent resistance, RTH. The same resistor value is basically used in both scenarios. Okay. So if we look, let us assume that we have a resistive network containing independent and dependent sources inside the box, and we can only observe two nodes, A and B. So from circuit theory point of view, if you are able to measure the voltage when there is nothing connected in between these 2 points, you are going to get some voltage value. This is called the open circuit voltage, because there is no load connected. So the voltage that you measure is labeled as open circuit voltage. This value is equal to the Thevenin equivalent voltage. Okay, VTH is just the open circuit voltage. When the circuit is running, operating, you can measure this voltage and record it somewhere. Then what we do is we make a short circuit between A and B, but we do it in such a way that we can measure the current flowing from A to B. That is, you put an ampere meter in between A and B. Now I can see I connected 0 ohms basically, so all the current that the circuit can provide me is being drawn through the ammeter, and I can read the amount of current that's flowing. That is a short circuit current. Okay, I measure the short circuit current and I measure the open circuit voltage. Their ratio gives me the equivalent resistance of this complex network. Okay, that is, the Thevenin equivalent will be equal to the VTH over ISC, which is basically the measurement that we have done in the open circuit case. So in practice, it's very easy because you use a voltmeter to measure the open circuit voltage, and then you use an ammeter to measure the short circuit current, and you record the values and calculate the equivalent Thevenin resistance. Then you can easily model the whole complex circuit with a single voltage source, independent voltage source, and an equivalent resistor, RTH. So this is how you do it in practice. You assume that your circuit is composed of like lots of sources, resistors, and complicated connections, but you put it into a box and you only focus on the terminals that you are supposed to deal with. And then from that perspective, you create a simplified circuit model, including one voltage source and one resistor. Now, once you have it, you can use the source transformation to transform this equivalent into a current source in parallel with resistor. The resistor value is same, and the current value should be VTH over RTH. So that's called the Norton equivalent. Okay. Basically, remember, the Thevenin voltage equals to the open circuit voltage in the original circuit, while the Thevenin resistance is the ratio of the open circuit voltage to the short circuit current. It's very easy to measure in practice, but theoretical calculations require a bit more effort if you need to solve it on paper. So let us take a closer look and study this new concept through an example. Here we have a circuit. As you can see, there are two sources, one voltage and one current source, and three resistors. Now I have these terminals and I'm interested in this terminal behavior. So I want to create a simplified model of this complex circuit. What I do is I just want to learn the voltage between VA and VB, which means VA minus VB. Since VB is connected to reference point, I'm interested in actually the VA. Now, VA is connected to this circuit node. Actually, there are 2 nodes here. And here, since there is no load available, the current cannot flow through the 4 ohms resistor. So its current is 0, which means that there can be no voltage drop. So whatever the voltage value is here at this node will appear at the voltage as a voltage at node A. Okay. So my purpose is to find the voltage at this circuit node, because when I'm measuring it with a voltmeter, it will show me that value. Well, we have the 2 nodes here basically, because there is no return path for the current to flow. So it's just dangling. It's just acts like a wire. As long as there's no current flow, I can measure the voltage. This resistor has no effect because the voltage cannot drop over it. The current is 0. So I have the node voltage. First node's voltage is 25 volts. I know it. The second node is unknown. Let's call it like the V1. Then I assume that the current is flowing in this direction for the 5 ohms resistor, and I assume that the current is flowing in this direction in 20 ohms resistor, and I also have an incoming current. So the sum of all currents must equal to 0 at this circuit node according to the Kirchhoff's current law. So I write down my currents. V1 minus 25 over 5 ohms gives the current that is moving out of this node, and V1 over 20 shows me the current that goes into the terminal, reference terminal. And minus 3 amps is entering into the node. That's why it has a negative sign. So with single equation, single unknown, I can solve my unknown as V1, which will equal to 32 volts. So I know that the voltage across this current source is 32 volts. And the voltage that I will measure with my voltmeter when I connect it between terminals A and B will be this value, because there is no current flowing. Because voltmeter acts like an open circuit because it has infinite resistance ideally, or very large resistance. So there will be no current flow through the voltmeter to the terminal, reference terminal. So what I'm measuring is actually this internal 32 volts that's of interest. Now I have found my Thevenin equivalent voltage. But I need another thing. I need to calculate the equivalent resistance seen between A and B. This is a box, okay? I cannot see inside. We know what is inside, but since I cannot see, I have to rely on my measurements. So we connect a short circuit between A and B. Now there will be a current flow and there will be some voltage drop, okay? Now I somehow need to calculate these short circuit current. How can I do this? Now my circuit, my new circuit, has one, two, actually, yeah, one and two nodes because this is connected to the reference node, right? So the voltage is zero actually on this side. I can assume that. Now, so if I find the current flowing through 4 ohm resistor, it will be equal to the short circuit current. And since I already know the voltage, I can find this V2, like I can find the V2 and I can find the short circuit current, and their ratio should give me the Thevenin equivalent resistance. So I can rewrite my circuit equations. Okay, now I labeled this as V2 in the second case because it will be different. The circuit is different, as you can see. There is the open circuit, here is the short circuit, so its value will be different from the previous one. So I have to resolve the circuit. So I'm assuming the same directions for current, and for the 4 ohm, I'm assuming that the current will be from left to right, okay, because the short circuit current enforces it. So if I write the first current, it will be V2 minus 25 over 5 ohms, leaving this node, so it has positive sign. V2 over 20, moving towards the reference node, would give me a positive part. And since the minus 3 amps is entering into this node, I'm going to get a minus 3. And I have the fourth component because I have short circuit the circuit. I have another current that's flowing V2 over 4 ohm equals to 0. Now, if you take a look at this, I have one unknown and one equation, so I can solve it. Here, if you do the math, you are going to obtain 16 volts, as you can see here. Now, I can also calculate the current because I know the voltage, I know the resistance. So the current of this resistance will be equal to the short circuit because, you see these connections, they are series connected, so they share the same current. If you do the math, 16 over 4 will give you 4 amps, okay? Now, I know the 4 amps and I know the VTH from the previous measurement. Remember, I'm not using the V2 here. I have determined the short circuit current, it's 4 amps. And I have determined the VTH from my open circuit measurement or calculation. Then their ratio would give me the Thevenin equivalent, which is 32 over 4 amps would give me 8 ohms. Basically, it's ohms. There's some, wrong thing that needs to be corrected here. And I can redraw my circuit as 32 volt voltage source with an 8 ohms resistor in series. Now this circuit and this circuit behaves equivalent from terminal AB point of view. What we have done is, if you have a black box, if you have an unknown circuit that you can only observe one or two nodes, basically you need two nodes, you can create this equivalent circuit without knowing the internals. What you need to do is you need to measure the open circuit voltage and you need to measure the short circuit current. Then you have your Thevenin equivalent model. This is very easy in practice because you can use a multimeter or voltmeter with an ammeter to measure everything. However, in theory, when we are working, we have to deal with equations and calculate those things by hand. So it's harder in theory. However, it's very easy in practice. So this thing is used a lot to reduce the complexity in order not to deal with the whole complexity. If you are only interested in the terminal behavior, Norton and Thevenin equivalents are perfect tools to minimize circuits This basically gives us the power of abstraction, so we can simplify complex behavior into things that we know very well and we can play very well. And you can further create an Norton equivalent. So we know that the Norton current source should have VTH over RTH, which is 4 amps. So if I can remodel this using a current source, 4 amp current source, with an 8 ohms resistor in parallel with it, between the terminals A and B. And that would make the Norton equivalent. If you know the Norton equivalent, you can create the Thevenin equivalent. If you know the Thevenin equivalent, you can create the Norton equivalent by source transformation. So this is, as I mentioned before, it's a bilateral relationship, which makes life easy. Depending on the scenario, you can use whichever one provides more advantage to you. All right. Now, if we approach the problem using the Norton equivalent, as I mentioned before, I can create this, I can transform my Thevenin equivalent into a Norton equivalent circuit as well. Now, in order to find the Norton equivalent, first I can transform the voltage source inside my circuit into a current source using the source transformation method. So I have 25 volts here and 5 ohms here. If you divide the 25 by 5, I need a 5 amp current source to replace this. And I put this 5 ohm in parallel. So the series connected components are parallelized. Now, if you look at the circuit, our original circuit and this circuit are the same from circuit theory point of view. They behave the same. Now, it's easy to write down the KCL and equations or minimize this circuit. I can simplify it into a circuit like this, okay? And again, I can create another source transformation. Now I have 8 amps, and when the 8 amps is flowing, I will have 32 volts equivalent of voltage source with a series resistance of 8 ohms, okay? Because I will put the 32 volts in series with 4 ohms, and there is another 4 ohm here. I can combine them into an 8 ohms resistance as they are series. So this will actually give me the Thevenin equivalent, as you can see. And from here, I can retransform it into the Norton equivalent. So as I mentioned in the previous slide, we have 32 volts here. So it corresponds to 32 divided by 8 ohms current source, which is a 4 amps current source. It's directed upwards because the current now will become downwards here. So it will create the positive to negative like polarity, the same polarity of 32 volts. And the 8 ohm resistor is transferred here. The only thing you need to calculate is make this conversion from voltage to current or current to voltage and change the circuit topology. So this circuit and this circuit are the same. And this circuit and all of them behave the same from a terminal point of view, which is the AB perspective, okay? This might be a bit of, confusing, but if you follow the book and solve some, examples, you will get the idea and you will appreciate it because it makes life pretty easy, especially from practical applications point of view. It's a very powerful tool that allows us to handle very high levels of complex circuits, simplifying them to single sources and resistors, okay? So basically, when we are trying to find the computation for the open circuit voltage, you don't touch the circuit. Basically, you try to determine the voltage at this between the nodes A and B. Once you have it, if the circuit doesn't contain any dependent sources, what you can do is when you are calculating the equivalent resistance, which is the RAB, looking into the circuit from the AB terminals, okay, you can replace each independent source with its equivalent, okay. So a voltage source can be replaced by a short circuit, and the current source can be replaced by an open circuit when you are trying to calculate the Thevenin equivalent resistance, okay? If you do that, the circuit here will be transformed into a network of resistors, okay? Then I can easily calculate. I can see that the 5 ohms and the 20 ohms are in parallel. I can calculate their equivalent resistance as 4 ohms, and 4 ohms here are series connected. So the RAB would be 8 ohms, which is also equal to the RTH. Now, if the circuit contains dependent voltage sources or dependent current sources, you cannot replace them with the short circuit. In that case, what you can do is you can always replace when finding the RAB. You can always replace these independent sources with their equivalents. That is, you can deactivate them. Basically, you remove them. But since you will have dependent sources, what you do is you connect an theoretical current source or a voltage source between A and B, and you try to solve the circuit. You try to determine the voltage VAB, and you try to determine the current through the source that you have connected. Their ratio will give you the equivalent resistance, which will be the Thevenin resistance. For the circuits that contain only resistors and independent sources, the approach makes life very easy. But if you have dependent sources, then you cannot replace them. You cannot deactivate them. You have to then put a test source, give it a name like VS. Okay, so it will have a current IS. Our purpose becomes finding VS versus IS, because that is the resistance basically, and that's the equivalent resistance, which would be the Thevenin resistance. We write down our equations and we try to obtain a function that is, we try to find the ratio of the Vs over Is throughout the circuit equations. When we have them, it means I have found the RAB and I can model the behavior. So calculation of the Thevenin equivalent requires 2 iterations of solution. The first one is to calculating the open circuit voltage, which is easier than finding the resistance. You can simply solve the circuit as is and determine the voltage between these nodes. But for the equivalent resistance, it requires more effort. You have to replace the independent voltage sources with short circuits. You have to open circuit all the independent current sources. You cannot touch anything else. And you have to calculate the equivalent resistance. If there are dependent sources, then you have to connect either a current source or a voltage source, and you have to find that V over I value in such a way that it will give you the equivalent resistance looking into the circuit nodes A and B. That will be your Thevenin resistance. Once you know these 2 things, you can easily construct your model. Now, in practical circuits, this is easy. 2 measurements and you have it. But in theory, you have to solve the circuit, okay? And 2 times. Once for calculating the voltage, then you change the circuit topology accordingly, and then you try to find the resistance using the approach here, okay? Once you know these values, the voltage and the resistance value, you can construct the Thevenin equivalent, and then from there, you can basically transform or find the Norton equivalent as well using the traditional source transformation approaches. Another topic that is important to us is the transfer of maximum power. Now, why this is important? First of all, from efficiency point of view, if our aim is to transfer energy in electrical form from one place to another, we want to be able to transfer maximum amount of energy to the other side, okay? So we need to develop the theoretical basis or philosophy for this. This is especially important for power utility systems that we use to power up our cities. You know, dams generate electricity, and long wires in the excess of kilometers, thousands of kilometers, carry this energy to cities, and then these are applied and used in the city. So we don't want to lose a lot of power for heating up the wires. So how can we transfer maximum amount of energy from a source to a load, basically? Okay, source generates the energy, and load dissipates the energy. So how their resistances or their impedances, in more general term, should be related to each other. Another scenario is not this much big scale, but there are lots of instruments that we use on a daily life, like our radios, like our cellular phones, and when they are communicating, they use again power transmission, like in terms of microwaves or high frequency sinusoidal signals. The problem is the same. We would like to use our maximum battery juice to efficiently communicate in long range. For that, we need to transfer maximum amount of power. We don't want to dissipate or waste it, basically. In communication and instrumentation systems, these are also important. So we always want to transfer the maximum amount of power from a source to a load. But how can we find a guide that will help us to in circuit design or in circuit analysis? Okay, let us assume that we have a box that is composed of linear resistors and independent sources of voltage and current, etc. An interconnected network. Previously, we have just learned that we can model this complexity. We can model all that topological complexity by a single voltage source and a series resistor. And we know how to do it precisely. Once I can model that circuit, then my problem in theory can be simplified to a circuit that I have already learned, basically a voltage divider. Let us take a closer look to this problem. Okay. Now, I know that I can basically replace the circuit, that complex circuit, with its Thevenin equivalent. Okay. So at the end of the day, I have some VTH and I have some RTH, calculated, measured, whatever. And I have some load here. If they are connected like this, there is a loop current. With the KVL, I can determine this current. And once I know the current, I can also calculate the voltage across the load, because this is a voltage divider, right? RL over RL plus RTH times VTH gives me VAB. So that will be the voltage across the load. And I also know the current. And if I multiply the two, what will I obtain? The power. The power of the load. Great, then let us do it. So in either way, you can find the current, take the square of it times RL, or you can find the voltage and the current. You can multiply them both, whatever. You will end up something similar to this. Okay, VTH over RTH plus RL square times RL. Now, the question is, we cannot change the RTH, we cannot change the VTH, because it's coming from the unknown black box resistive network containing independent and dependent sources. It's the dark side, we cannot touch it. Now the question is, for which value of RL this power is maximized? Now let us go back and think in our calculus pants, okay? I have a function P and I have a variable. I can choose RL as a free independent variable, just like X, okay? So if this is the case, it's going to be a function with a single variable. Now what I'm trying to achieve is to find the maximum point, that the maximum value of this function, P function. For which value of RL can I maximize? I can maximize the P, okay? This is a basic problem, optimization problem, that you have maybe seen different versions in physics or in calculus classes. Well, the expression might look ugly, but all other things, all the variables other than the RL can be treated as constants in this specific scenario. So if we take the derivative with respect to RL and if we equate it to 0, then I can obtain the following expression. For those who doesn't want to take the painful path, you can use the symbolic toolbox of MATLAB to do the math for you. You can take the derivative. You just need to define the variables, and then you take the derivative with respect to a single variable, and it will give you some result out of it. Okay, you can make use of the help and document for that. Anyways, now the p is maximized when the derivative is 0. So I look at this expression. My variable is RL, and I have RL here, RL here, RL here. And I also have some in denominator, but this cannot be easily 0 unless the RTH is negative, which is unlikely. So I will focus on the denominator. If you do this math, if you equate this to 0, VTH is reduced. And at the end of the day, if you do the further simplifications, like this and that square will be simplified. So RTH plus RL equals to 2RL. Then I move the unknown RL to the right-hand side. Then RL equals to RTH. Interesting, right? What we see here is that in order to transfer maximum power to a load, the value of the load should be equal to the Thevenin equivalent resistance of that circuit. And in that particular case, the maximum amount of power that can be delivered to a load is given by VTH squared times RL over 2RL squared, which will give me VTH squared over 4RL. This is the maximum power you can deliver to a load in this kind of a scenario. This is the best thing you can do, okay? And we want to achieve this because if we are not able to deliver this, the excessive power lost is basically due to heating and other means. However, as you can see, this term is divided by 4. It's a huge, drawback. Like, I mean, that means it's not easy to deliver power basically because you are losing a lot. Even your maximum is not that maximum actually, as you can see here. Okay, so this is the primary result. Now, actually, in this, there is a more generalized version of it. Typically, we will learn about it in the near future, but it's worth mentioning here. We have actually impedances, okay? And impedance is a complex value. We only have real values. The resistors are just some integer or some floating point numbers, the real numbers that we have. In more universal expression, they are actually impedances. So R plus J times X, that X is reactance. And in that case, if we are two impedances, then in order to deliver maximum power, two impedances must be their equal to their complex conjugates. That is, RL should be equal to the RTH, just like this, but the reactances should have negative opposite signs so that they can cancel each other. Because when you have a reactance, that power will be lost. There will be some reactive power that is stealing from your energy source. In order to zeroize it, you need to put the opposite sign reactance with your load. This is especially important for factories where there are lots of reactive components like inductive machines, etc. Not that important for the home, especially in energy delivery, or for RF circuits. This is very important because you want to match the impedances for maximum power transfer. Otherwise, you will be losing unnecessarily, you will be wasting energy, and you don't want to do that. So a topic called the impedance matching, and is a field of research for RF engineering, for instance, deals with this kind of problems. For the time being, just remember that the two resistances, the RTH and the RL, should be equal for maximum transfer, but also keep in your minds that if they are impedances, their reactive parts should have opposite signs. If it's a plus X, the load should have minus X to counterbalance and to enable maximum power transfer. That's just an extra information. Now, there's another thing called the sensitivity analysis. Actually, we have learned how to do it with the help of LT spice, but from theory point of view, what we have done there, or how it's achieved, is sometimes we are interested in certain node voltages or mesh currents, whatever, some circuit variable, and you want to explore the dependence of that circuit node voltage to a particular variable. Typically, it's a component value. What happens if the component value shifts to my variable? This is called the sensitivity analysis. How it's done is basically you just try to first you try to obtain the node voltages, and if the voltage of interest corresponds to a node voltage, then you obtain the mathematical expressions like this. Okay, here this is the symbolic solution of the node voltage V1. With this kind of math where you can do lots of errors, you can always use MATLAB's symbolic toolbox. It will calculate this for you. Okay, Mathematica also can be used if you have access. Once you have this, now I would like to learn how this V1 will change with respect to a deviation in R1. You can take any of these resistances or any of these currents, any variables basically in this mathematical expression. That would be your independent variable. You can think of it like a function. Then you try to inspect the sensitivity by taking the derivative with respect to that chosen variable. In this case, I'm looking for the dependence of V1 on the variable R1, which is the value of this resistor. And I do the math by taking the derivative of it. Okay. Now, this equation basically shows me the relationship between the V1 and the change of R1. What happens if R1 value deviates? How much deviation will occur in my output voltage? How much will I get affected? Okay, this is an indicator for that. Okay, basically you treat all the other variables as constants, and you just consider R1 as your X, basically the functions variable, and you take the derivative with respect to it while treating the others as if they are constants. So looking into this, we have many different variables available. So we can define many different sensitivities. You can basically define many different sensitivity functions using this method. Of course, when you are doing this algebraically, it's a lot of pain. However, in simulations, we can also do this. Like when you design a circuit using SPICE, you can always get the sensitivity analysis using a similar approach. Some advanced simulator programs, they basically provide you a sensitivity simulation. So you just say that I'm interested in this voltage or current value, and then my independent variable is this. Can you show me how they are related? So it gives you the trends or the potential of change, or basically this is what we call the sensitivity of that output variable with respect to an input variable. Okay, you can set anything as output variable and you can choose anything as an input variable, but one at a time it can show you. And in Monte Carlo analysis, which is the statistical approach, it will change everything. All variables will be changing according to some Gaussian distribution or a uniform distribution. And then you can still measure your output, observe your output variable, and see what can happen in practice. Because here we are dealing with ideal circuits, but in real life, all the resistors, all the components have some deviations from their ideal manufactured values, and this will happen. So you want to make sure that your circuit performs under every condition as intended. So you want to see the performance boundaries. And we do this by making Monte Carlo corner case simulations. This is why at the very beginning, when we are dealing with the LT spice, I tried to give you a glimpse of it. Maybe it didn't make sense at that time, but I think it makes more sense at this point. Okay. This will be the last topic to discuss for today's class. In summary, up to now we have covered the basic terms for circuit analysis, the nodes, essential node, path branch, essential branch, mesh, and a planar circuit, the concept of a planar circuit. We learned about the node voltage and mesh current methods. In practice, we use node voltage more, but mesh currents are also applicable, and sometimes they are handy too, so it doesn't hurt to know. But the modern computer systems that simulate circuits, or we use to design circuits, typically use node voltage methods and modified node voltage methods to automatically solve a circuit with any complexity using the mathematics of linear algebra and matrix algebra, basically. Okay. I tried to show it a basic example with the MATLAB, which I suggest that you do try to solve some circuits with that MATLAB approach to learn more and to fortify your experience and knowledge in circuit theory. This chapter is very important as it creates the backbone of many things. There are many new concepts that are introduced to you, so you definitely need to solve a lot of questions. Please use my lab and solve those homeworks, not only for the points that you will get, but in order to understand these concepts, you have to get dirty and solve questions. So we also learned about source transformations. These are like the kung fu techniques to deal with circuit complexity. Then we have ended up with the wisdom of Thevenin and Norton equivalents, which gives us power to put all that complex circuits into a box and look at certain terminals of interest and model them with a single resistor and a voltage source, independent voltage source, or in series connected, or a current source with a resistance in parallel. Okay, we learned that every circuit somehow can be represented by that notion, and we can use this further, apply it to some theoretical problems such as the maximum power transfer, and find the conditions under which we can transfer the maximum power to an unknown load. What value of that load should have in order to receive the maximum power. So we know that for maximum power transfer, the load resistance should be equal to the equivalent Thevenin resistance of the source side circuit, whatever it is. There's another concept called superposition, which I'm not very fan of, because it's just a standard application of linear time invariant system theory. You can take a look at it in the book chapter, because it requires the solution of the same circuit many times. So you just iterate and iterate, then you sum the outputs, the solutions, to combine to find the ultimate solution. But the methods that we have seen so far can directly find you the exact solution, like the node voltages or the mesh currents. So it's a kind of a redundant thing which you can read. It's also only valid for linear circuits, but yeah, in real life circuits you will rarely find that linearity. It's just an assumption, but that assumption allowed us to develop these circuit theories and explore the methodologies in order to handle complex circuits. I don't, underestimate it. I respect it, but you can read it from book, and hopefully we will continue with the next topics ahead. So have a great week. See you next time.